new air conditioning. And we were able to save nearly the entirety of the original structure of the building. So here again, another view shows those robust finishes. So the board-formed columns, columns, beams, and ceilings, and we did a polished concrete floor. And the floors had up to 8 layers of floors stacked on top of each other in this building. So the idea was that what we had to do at this 100-year renovation, the owner should not have to do again. So it's these finishes were brought back to a very like an appealing finish and one that could serve as the final finish for a sort of specific reason. And we see it as like a reinterpretation of like a brick and beam building, which are sort of appealing that you have sort of the exposed wood, the exposed brick, and it's something kind of approaching that, but in concrete. So there was lots of work to get the building to that state. And we looked at them through a climate and carbon lens, sort of retrospectively, like we had an intuition about it, but we did this study as part of a presentation that came later. And so the idea here was that we can avoid contributing more to climate change in the repairs. And we could also be responsive in the way that the building operates. So one of those ways, there's three sort of sub case studies. One is structural repair, one is the tenant fit outs, and one is the building envelope and operational energy, which I'll talk about towards the end of the presentation. So the first was the structural repair. As I mentioned, the systems weren't really working. So the building had deteriorated in some significant ways. The floor slabs had been steamed in the ceilings, concealed because of some leaking steam pipes. So the steam radiators were leaking, the slabs were getting steamed, and they had extremely low compressive strength. They were also one-way slabs. So what it means is that from beam to beam, if you can see where my mouse is, the perimeter radiators had steamed those areas. And because they weren't able to span in another direction, we would have had to remove the entirety of that slab from beam to beam unless we were able to introduce a secondary support. Yeah, this is a better view. So this shows the extent of concrete that would have had to be replaced, like cut out and replaced in patches to allow for the replacement of that or the repair of that floor structure that had been steamed. By introducing secondary structural steel, we were able to vastly reduce the amount of concrete that was used for those repairs. And so what that means from a sort of climate point of view is that the upfront embodied carbon was reduced by about 79%. So on the left here in the bar chart is the option with structural steel being added. So you can compare the structural steel in both of those scenarios, and it's obviously that has a much higher embodied carbon, and on a like sort of per unit basis, but because we were using more of it, but relatively less than concrete, and also able to leverage more of the existing concrete that was already there. Because not all of it was deteriorated, it was deteriorated in specific sections, very close to the mechanical system. So this was one way we were able to realize significant reductions for like a specific repair. And here you can see the result of that. So on the octagonal columns at the front facade of the building, you can see the new steel collars that support the steel beams that run back to the beams, and then the east-west supports that span between those beams, which allowed us to replace the section of concrete nearest the windows, which is what was affected by the radiators themselves. The next aspect was tenant fit-outs. So this is a demolition plan / before plan, which shows the sort of subdivision of these units. There was a lot of material that had gone into renovating and re-renovating these spaces into smaller and smaller units. So these are 6,000 square foot floor plates. Sometimes they would have they would have up to 13 tenants. So it was difficult to manage. And it was not good for the building. It was like with that sort of level of complexity, I think that there was a little bit of a loss of control with how people were implementing new building systems, like running pipes through floors. So um, to sort of stop that, well, I'll talk about what we implemented, but this gives you an idea also of starting to pull all of that out of the building. There was vast amounts of material that had to come out. And so it became the same kind of thing. Like, how do we prevent this from happening again in 100 years? Goes back to what I mentioned about the base building finishes. Um, is there a way to make this building flexible for its occupants, but not so wasteful? So we did that through both the planning and some guidelines that were set in place. So the idea was that those finishes that I mentioned um, would remain exposed. Um, and you'd have sort of a flexible space that could be outfitted with furniture. And then to the south, where the HVAC has to run because the building wasn't built for that, and that like you need to lower the ceiling in specific areas for that. Um, that area becomes where it becomes subdivided, and interventions can happen that can kind of change the space, be a little bit smaller. But it reduces the impact of sort of like successive fit outs. And the reason for that was that we did a quick study on what a typical floor fit out in the sort of pre-renovation scenario of this building would have looked like. And we looked at just three basic materials and we found that it was quite a big impact. So glass wall for sort of like glazing inside, a gypsum ceiling, and then a gypsum board wall. And just using that, like there's so many more materials that go into a fit out. But we were seeing like 1 million kilograms of CO2 equivalent, which is pretty significant in the context of like those once in 100-year renovations. This is actually like quite a large impact, and the assumptions are quite light. So this is averted embodied carbon. So these are implemented through tenant guideline for fit outs, which restricts the extent of renovation allowed in the space. And the idea is that fit outs can happen with the furniture of the space, which can have a secondary life through resale or tenants taking it with them, but the building stays more or less stable. So you can't add tile to the concrete, which would necessitate that that would be removed later and the floor would be damaged. Can't add drywall to cover the ceilings or columns. It's trying to make those finishes sort of an appealing aesthetic so that you don't have to add, and you can add through furniture, which again can be removed later. And so the building also has systems which have been designed for full floor tenants. And so we'll get into that further as we get to the detail level. But first off, as mentioned, the building was in really poor shape when we started. So this was an evaluation we did of the brick. And what was really striking was that we noted the lintels of almost all of the windows were having issues where cracking was prevalent. So looking closer, we recognized that the lintels had deteriorated significantly in almost every window. And they were rust jacking and cracking the brick. The steel supports were flaking in really large sections. Um, and we determined that that was because of the roof and parapet detail. So the roof had failed, again, was not maintained well. The parapet had also failed. The roof had sort of pulled it in, opened things up a bit, and water was getting in. So through cracked stones or just sort of through sitting on it, it was getting into the wall, running down inside the cavity of the brick wall, and then rusting those lintels out. So as you can see on the left, what kind of extent that led to in terms of repair was the entire perimeter of the lintels were removed and replaced, which was a big job. And again, became about how can we avoid that happening again. So there was an extensive build out of the parapet. So the stone caps remain, but they've been flashed. There's a space behind the wall to dry and drain into the roof, which is below these pavers. So the pavers serve to protect the roof. The lead coated copper flashing just pokes over the edge of the stone, so it's there but subtle, but does the job of protecting that wall from water infiltration again. Um, and then we so beyond that, we started looking at how to make the building like function better. So we did a base building model and an energy model as part of looking at the different options for the retrofit of the building. And again, this was sort of retroactive. We had we didn't have the either the client will or the budget to be able to upgrade the envelope um, in a way like to add insulation. But we looked at updating it or upgrading it in different ways, which I'll talk about. So um, we looked at three different scenarios. Uh, the existing building envelope as is, existing building envelope and upgraded windows, and then an upgraded building envelope and upgraded windows. And we looked at all of those in an embodied carbon and operational perspective. But I'll talk about the mechanical system first. So it's sort of to get back to the resilience discussion. Um, we the building, as I mentioned, was very uncomfortable. So part of the system was using existing boilers along with a new radiator system, but also the building had to provide cooling. As I mentioned, some people had or some tenants had just kind of provided their own cooling, and it was a sort of free-for-all system that was adding a big energy demand to the building, and also not very efficient. So the idea was to add cooling. So it's electrical cooling, packaged heat pump. Each building or each floor has its own unit. Um, the mechanical is all pre-routed, so tucked in between the beams so that it can maintain a higher ceiling height, whereas the trunks run in a corridor that's to the south end of the building where there are no windows. So that's where the ceiling drops the lowest in the service corridor where you access the washrooms and exit hallways, and the rest of the spaces are sort of kept high. And you can see that here, that mechanical um, running up above the beam level, the lights below that, so keeping the ceiling visually much higher, much more appealing than it looked before. The other component of the mechanical upgrade was um, the old system on the left. So this was just showing some of the redundant steam piping that had leaked and steamed those slabs. Not very well maintained. But the idea again was to sort of learn from what had happened previously. So where it had leaked, concealed in the ceiling, and no one was able to see it, the exposed finishes allow you to identify a problem much more readily and address it rather than it sort of festering in the walls. So the idea was that each floor had the piping that served the radiators on that floor. So you can see in the image on the right, there's two runs of supply and return piping that run below the actual supplies to the radiators. And so that was so that if there is a leak, you're able to see it. It hits the floor, you clean it up, you shut off the system at that floor, and you're able to fix it. And it's not kind of hiding behind a drywall ceiling and you're identifying it too late. So it's all with the sort of intention of reducing the amount of material that has to go into repairs over the next 100 years of this project. Another big item was the windows. So as I mentioned, the owner had wanted to replace these. They're the original steel windows. They were a little bit under-engineered for when they were built. So what that meant was that the stoppers were not adequate and the windows would sometimes rack and twist in the wind. So if you didn't have it kind of, if you had it open past a certain point and the wind caught it, it would slam open, shatter against the against the brick pilaster and rain glass down on one of the most active public squares in Canada, which is not ideal. So there was proposed changes for that. But looking up close, you can see that there were haphazard renovations made to these aluminum sliders inserted into panels. Some of the operable panels were cut out. They were painted a beige. They were let rust. They had ceilings dropped in front of them, as you can see, and some just had panels sort of blocking them out. So I mean, it's easy to see why that was the assumption that they had to be replaced. But we went through a very careful assessment, and I'm going to speed up a little bit because I think I'm going too slow. But we went through a careful assessment that looked at each of the windows. So the red here was just showing that maybe an operable panel had been removed, but largely we found that the frames were in very good condition. And they needed tweaks. So we didn't need to go to a whole new window. These windows had already lasted 100 years and they could last 100 more with the proper care. So this is the result. They still have operability. The upper windows have the awning and the lower windows still have two casements. You'll note that we added some additional stoppers to prevent them from racking and twisting. But largely those windows, all it ended up being was removing surface rust, painting it, replacing the glass, fixing the operation, and then some minor details that help with some sort of long-term issues. So we did just window details for existing details, and they're really quite simple, but they helped a lot with some of the issues that the building was facing. So in one case, the sill was rotting, or in many cases, the sills were rotting because you'd have air condensing on the glass, running down and hitting the sill. And so those wood sills would deteriorate. All we did was pull the wood sill back a bit and added a metal strip that allowed that humidity to just evaporate rather than sit on the wood and ruin it. And then another important aspect was we knew that the plaster walls are actually like pretty high performing. So a cast in place building with plaster walls, in theory, should be somewhat airtight. But there was a big issue around the windows. The plaster went right up to the frames, and because of expansion and contraction, that meant a lot of cracking. So a really very simple detail was to pull the plaster back a little bit, provide like a clean edge detail, and then provide a space for sealant. So it was just something that cleaned it up. So you can see this little aluminum bead along here that provided an edge for the sealant and for the plaster to terminate it into. And so that I think actually had a huge impact. So going back to this energy modeling, energy modeling and sort of assessment of carbon, we're most close to scenario one here, where it was just replacing the monolithic glazing in the windows. In relation to these other two options, which have magnitudes greater of upfront carbon, they were predicted to achieve only marginal benefits over the first model, which maybe was an issue of the energy model. But what was most interesting was we found that with the relatively light measures that we took, the increased air tightness through repair of original plaster walls, the upgraded window performance through new glazing, gasketing, better airtightness, a low E coating, and the upgraded radiator distribution, which is still kind of tied to what was a relatively new natural gas boiler system, and unfortunately had to stay, but will eventually be replaced. Meant that we were, first of all, tied to natural gas. But with those measures, we realized an 80% reduction in natural gas usage, which I thought was pretty staggering because it was also beyond what the model showed. But I guess the point is that all of these scales connect. Policy enables reuse. Cities plan with heritage as infrastructure, or should. Buildings adapt with careful conservation, and details protect that work for generations and can help them adapt just at that level. And heritage is really the thread running through them. And I want to say thank you all for your time, and I'm happy to, I just wanted to provide my email if there's any questions or clarifications that anyone wanted to send, but I think we have some time for questions as well. So thank you all.
Thank you, Michel. I'm really impressed by the project details and analysis you developed on Herman Picnic, and also the research and comparative illustrations on carbon studies. So it was really interesting for me, and I'm sure for the others as well. It's a new perspective here. Actually, I have one question, but let's see if others have any questions here. In Q&A sections. I really appreciate if you write it in the Q&A section if any questions. So I will ask mine, so then we can check for the others.
Sure. Okay.
Thank you. In the Herman project, and also in even low rises built heritage, usually you can see that it's developed like a thermal breeze from age and the past changes, or maybe from that time, because of the lack of best material that they can use, and this leads to energy loss. But and to fixing them and kind of restoring them, or any preservation process can affect the building's character or the fabric of the building. And what strategies would you recommend for managing thermal breaks in the way that they improve the energy performance while minimizing the changes to the or building heritage value? Maybe in like the Herman one, it would be a very huge, because the building is in huge shape.
Yeah.
But or even in the low rises is different because we have the huge number of them. So what's your suggestion for these kind of thermal breaks that may happen, or it's emerging in these types of buildings, in the built heritage in general?
I think that's a pretty difficult question. So Hermit specifically, it's nearly, it would have been impossible to eliminate the thermal bridges. It's because it's a cast in place concrete building. It's got basically like those lintels that I mentioned were just steel shelf angles that were bolted directly to the concrete right at the slab level, and it basically translated heat directly in. So there's no real way to, I mean, there's a way to eliminate it. I think you would just end up reducing, like you'd have to do it from the inside. Probably like bring the insulation further in on the envelope, like along the ceiling. So I think the interior is probably the way, is usually the way to do it. In Herman, that's where we would have done it if we had insulated the building. So it like the plaster wall wasn't a heritage feature. We kept it because it had historic value and because it was able to make the building more airtight, and the owner did not have the budget to insulate the building, and it wasn't a sort of requirement because of the extent of the renovation. So yeah, I think the interior is sort of the key, but difficult, especially if there are other features in there.
And as you have done the process of and then an energy assessment for the Herman building. Which one of the it was the windows, or maybe what was the key point for for energy loss at this scale of the building? For this kind of energy assessment and or maybe thermal bridge as you see and for
So
insulation.
as I mentioned, I think we had done the energy modeling, and I think I, it was a while ago, and it was with it was doing it for a study, so it wasn't part of the project, and it was sort of someone helping us on a pro bono basis. So I think the energy model may have been a little less accurate than we wanted it to be, and maybe assumed that the building wouldn't have been able to achieve the level of performance it did. So like as I mentioned, it became it became a lot more airtight, we think. We haven't done an airtightness test yet to validate that, but um, it's interesting that with just relatively simple measures like that reduction of 80% of natural gas usage, like it was showing closer to 50% on the energy model. So like there was quite a bit more in reality that was actually achieved, which I think maybe is it's at least an interesting thought about our energy model for this project, and maybe all energy models. Yeah.
So, yeah.
That like I think okay, I guess to sum that up, what I'm thinking is that post occupancy valuation to actually validate how these things work is probably equally, if not more important. If we had shown someone that it was only a 20% reduction, let's say, and that meant that the windows got changed, we never would have known that we could have got 80% with just these minor changes. So I think a post-occupancy evaluation, which is something that we're hoping to do and trying to look for a way to do that, um, like will actually show that maybe the extent of renovation um, doesn't always need to be so extensive. Like, of course, there are situations where it doesn't, but this particular building might have had features that helped it with that. So one of those was the plaster walls. It has a really excellent window to wall ratio that helps mitigate solar gain, and uh, like the walls still being like 18 inches thick, still have some thermal performance value. So they help with heat loss and things like that as well. So I think it's complex,
Yeah.
which is a non-answer, but
Yeah, actually, I think it's very hard, to modeling the whole built heritage an energy analysis and a kind of, it's very easier for the modern architecture, but in the heritage they are kind of different, and it's very hard, maybe time consuming. And we have a kind of, I think it's not a question by Jeff. Hello, Jeff. Nice to see you here. It's wonderful thoughtful presentation applying heritage principles from large-scale planning to building details regarding the Main Street planning. Note that heritage planning moved to multi-lit properties on many main streets in Toronto. The status is now under threat to the Bill 23, and it's 1st of January 2027 deadline. Yeah, no, it's not kind of question, but yes, kind of. You have this, Mitchell. Yeah.
yeah, I saw.
Yes,
Yeah,
thank you.
it's unfortunate, but I don't know. Unless Bill 23 changes.
Yeah, yes. Another question by Ali Bali. Any idea on how to improve this project with modern AI models? Yeah, Ali is a kind of a computer science
Hmm.
person. He's asking about, so yeah, that's great. So, um, do you have any
That's
idea?
so not really. I mean, like from what I understand, AI is only as good as the information you put in. So I think again, it kind of goes back to something like post-occupancy evaluations. Like we need that sort of body of knowledge, like a ton of buildings that have been retrofitted in a sort of simpler way, see how they perform, um, and then can that be used to help predict, like build an AI model to help predict? I guess that's how I would imagine it would be helpful.
Thank you. And any other questions? We're almost in 1 p.m. So if there isn't any, I want to. Oh, yes, great project. Energy audits should be required for all renovations. Oh, yes, we have a question by Megan Hobson. Great project, energy audit. Can you see it?
Oh,
Michelle,
yeah.
or,
So energy audit should be required for all renovations. Any idea how we can make how we can make that part of all renovations? I think it's always regulation. Like we had to do our energy model following the project and with the help of generous engineers who would help us with that because if it wasn't required, the client like they already had a limited budget and didn't want to pay for it. So if there's policies in place that require you to actually check these things, and it's part of the process to reuse a building and prevent its demolition, I think that's where they're extremely valuable because it's possible to make a building a lot better.
exactly. So thank you, Mitchell, and thank you, Megan, for your question. I think there's no more question here, and we're running out of time. So thank you, Mitchell, for this exciting presentation. It was so interesting. And if anyone has any questions, you can just send it to me or send it to the CPHD's email. So all channels are available for any question, and I will pass it to Mitchell. So thank you very much. Thank you, Mitchell. Thank you for
Yeah. Thank you.
great presentation, and thank you participants for having time to this presentation. So thank you all, and we're looking forward to our next speakers. And then perfect. Thank you very much. Thank you,
Thanks,
Mitchell.
everyone.
Thank you, Alirza. Thank you, Bruno. Thank you, Carlos. Thank you, Eric.